Okay, this enrichment activity is actually the lab that you would have been performing in small groups during our unit on vectors. And this particular apparatus here that I'm going to take you through is called the force table. And then there'll be a follow-up lecture after I'm done explaining how this works to go into the particulars of what you're going to do if you want to participate in this activity here. Now you can see that we have a round tabletop here. It's highly reflective so that I have this angled in a particular way, so hopefully you can see that. I don't know how clearly you can see this, but around the edge are 360 degrees marked off so that we can know particular angles. 0 is right here where my finger is, and then going counterclockwise here, it comes all the way up to 360 or back to there. Now you'll notice that there is a little ring here. It's a little transparent plastic ring, and it's got 4 strings coming off of it. And there's a reason that there's 4. Now the main attachment points here are these little pulleys. And with these pulleys, what we can do is we can secure these onto the edge of the ring, and they have a little marker so that we can put them pretty accurately at any degree angle we would like, and then we can put a string draped over the top, and at the end there's a little paper clip there, and we can hang masses from this. So because of this little pulley clamp mechanism, we can convert the vertical force of the weight of one of these hanging masses into a force that would want to tug at the central ring at a given direction. Now, the idea behind this lab overall, and there are some parameters that you're going to have to follow, is that you are going to create a problem where you want to set up equilibrium, which means all of the forces for the strings tugging at different angles would add up to 0. And I'm going to set up a really simple scenario of this to kind of show you what the end point is. But very quickly, to give you a preview, if all of these tugging forces that act outward at different angles are calculated just right, so they add up to 0, this ring would sit right in the middle of the table. And it would not be tugged. Even if you moved it out from the middle, it would get pulled back towards the middle because that's where the equilibrium is at. So the general idea here for your enrichment activity is I'm going to give you some parameters where you're going to make up 3 of the vectors, and then you are going to have to calculate the 4th vector that is referred to as the equilibrant, which will make all of the vectors add up to 0. And then what we can do is we can actually test out your problem by coming to the force table and setting up the clamps at specific places, loading them up with the masses that you have chosen, and seeing if it actually works. So here's the simple scenario that I'm going to set up. I'm going to put each of the clamps at 0, 90, 180, and 3. What did I say? 0, 90, 180, and 270. And then we're going to drape these guys over the pulleys. And then what we're going to do is I have 4 100-gram masses, so we're going to have equal masses all at the 90 degree markers. Hopefully, from a common sense perspective, that gives you the idea that, oh, they're all going to pull equally up, down, left, right, and so nobody's going to win. So for example, if I just put 1 on here, you will notice, I'm going to have to hold on to this side, that this would want to be pulled in that direction because that's the direction that the pulley makes it want to move in. But if I put another one over here, you will notice that that wants this to pull over this way. So it's kind of like it wants to pull this direction because this one pulls out that direction, and if you remember your vector conceptual addition here, that means it wants to pull overall into this direction. So what we're going to be doing here is we're going to add some more onto these other. Now you'll see with these three, these guys pull equally that way, but we don't have anything to balance this, so it gets pulled almost directly in that direction. So now when we bring the last one over here and set it up, bingo. You can see, I'm going to steady these. You can see that the ring sits right in the middle of the table. And even if I were to move it out from the middle of the table, you can see that it ends up getting pulled back to the middle because that's where the equilibrium for this system is. Okay? So that's the way the force table works. And again, the basic idea of your enrichment activity is you are going to choose 3 masses to act at 3 angles, and then using vector mathematical principles, you are going to calculate what is the magnitude and the direction of the 4th mass. What does it need to be so that overall it brings the whole system to equilibrium, and then we can actually test it. And if you're going to do this, I'm actually going to set up a Google Meet with you so that we can do this live and you can see whether your solution actually does work or not. So I'm going to go in now and we will do the conceptual lecture about how you need to approach this and what are the parameters that I am setting on you for choosing your angles and masses, because I'm not going to let you choose like super simple angles that are easy to work with. So I'll be back in just a minute. All right, I'm going to keep time on myself here. Okay, here is your lecture about what you will be doing in this force table activity. Now, I mentioned in the introduction there that the idea is that we want equilibrium. And that's the big theme of this lab activity. And for equilibrium to be established, at least from a force perspective, we need the sum of all of our forces to add up to 0. Now, overall, you are going to have 4 forces because you're going to have 4 different masses hanging from the pulley clamp mechanisms. So we could talk about F1 being the force of one of those strings plus F2 plus F3 plus F4. We want all that to add up to 0 newtons. Now, in the end, the idea here is you're going to choose what forces you want to set up here, and then you need to find what the 4th force needs to be so that this is true. Now, the way to approach this is very similar to adding vectors together. So the idea is, and I'm not going to go into the explicit breakdown equations for horizontal and vertical dimensions here, or x and y dimensions, because you should already have that in your notes. But one of the things about our original statement here that is implied with if the sum of all of our forces has to add up to be 0, that means 2 things. That means the sum of all of our x components of those vectors have to add up to be 0, And that means that the sum of all of our y component of those vectors have to add up to be 0, because that's the only way that overall they all add up to 0. Now, if you remember this aspect of adding vectors together, if this statement is true, that means, and I'll call this horizontal, that means that f1x plus f2x plus f3x plus f4x all have to add up to be 0. And you have the equations in your notes about how to break these vectors, these force vectors, into horizontal and vertical components. Now I'm going to call this vertical again. So that means over here we would be saying f1y plus f2y plus f3y plus f4y all have to add up to be 0 as well. So as long as you know what the value, the magnitudes, and the angles are for f1, f2, f3, you can figure out all of these pieces so that you could, again, figure out what f4x is and what f4y is. And going back to basic vector addition, once you can figure out what f4x is and what f4y is, in order to figure out what f4 is, your last two steps will be the Pythagorean step, which means use the Pythagorean equation to get the magnitude of 4, and then 2, or I should say the last step, step 4, is the arctangent step, so that you will be able to properly figure out what direction does this point in. And remember, when you do the arctangent step, it is always the arctangent of the y component over the x component, and based upon the sign pattern of your x and y components for vector 4, that will tell you whether you're pointing into the first, second, third, or fourth quadrant, which means you might do nothing to the answer on your calculator, or you might have to add 180 degrees, or you might have to add 360, depending on what quadrant your answer points in. So that is the basic concept behind our force table problem. So again, to summarize, you're going to choose 3 force vectors, and then you're going to figure out what this fourth one is. And when we go to test it, what we're going to do is you're going to tell me what your 3 chosen ones are, and I'm going to set that up on the force table. Then you're going to tell me what your fourth one is, and then I'm going to put that on there, and we're going to see if that ring stays right in the middle of the table. Okay, so I'm going to erase this, and we are now going to give you some parameters for choosing your vectors. How am I doing? I've only taken 5 minutes. This is good. Okay. So here are your limitations. All right? Remember, you have to choose, F1, F2, F3, then solve for what we're going to call F4, but remember all of them have to add up to 0, as I described in the prior segment. Okay, here are your limitations. No 2 vectors can be a multiple of 90 degrees apart. Okay? Another one. No 2 vectors can be within 15 degrees of each other. Okay? A third one, no vector directly direction can be within 10 degrees of 0 degrees, 90 degrees, 180 degrees, or 270 degrees, okay? As you can tell, I'm trying to get you to use oddball angles here. Okay, we continue. No vector direction. Can be a multiple of 10 degrees, 30 degrees, or 45 degrees. Okay? All right. Magnitudes of all vectors must be a multiple of 10 grams. Now I'm going to talk about that in a moment. And between 50 grams and 150 grams. Now, technically, we are adding forces together here, but the way that hanging a mass becomes a force is that the pull of gravity causes the downward force of the weight of the mass to be converted into that horizontal force that tugs on that center ring of the force table. So in the end, because gravity is acting on all of the masses hanging on the off the pulleys of the table, we can go ahead and treat the mass that's hanging on the end of the string as if it was a certain amount of newtons. So we will be processing this with the unit of gram. And magnitudes of all, and I'm going to call these chosen vectors, must be different. Okay? So, when you are coming up, I mean, literally, if we were going to write what we would call F1 here, it would be a certain number of grams at, we'll call it theta 1 for force 1. For force 2, when you choose it, you're going to choose a certain number of grams, and it's going to be at a second angle. And F3 is going to be a third number of grams, and then there'll be a third angle. And so the numbers that you put in here and the angles here must kind of fit within those parameters. So you can tell I'm really trying to make you choose, especially when it comes to angles, no easy, trigonometric angles, which is specifically the most directly related to the 30 degree, 45 degree, and you can't be right on one of the axes, and you can't be super close to one of the axes. Okay? So, again, your problem is you choose 3 vectors, then solve for that F4 according to what I described earlier, and then when you are finished, you can let me know if you would like to actually see whether or not your solution works on the force table. Get in touch with me and we will set up a quick little Google Meet where I can have you check in. I'll have the force table here. You can tell me what your 3 chosen vectors are, and I will set those up on the table, and then you can tell me what you have calculated your 4th one to be, and I will put that on the table and we'll see if it worked out right or not. Okay? So that's your enrichment activity from the vectors unit. If you want to go ahead and give it a shot, and then I'll just wait and see who feels like doing a little over-the-top work with that. All right, thanks for hanging in there. I think I did okay. I think we're under 20 minutes. Excellent.